these talks online like this. So here's hoping we get through with the technology. So thank you very much for the introduction, Hannah. It's a real pleasure to be asked to give one of these talks. What I'm hoping to do here is just give a flavour of some of the work that we're doing in the group that I run at the University of Strathclyde. As you can tell from the title, we're interested in use of optics to understand how light propagates through the ocean and how it influences physics and biology. So a wee bit about myself as background. I'm an optical physicist. I did a degree in laser physics and optoelectronics. That was at the University of Strathclyde, and I'm still based there to this day. As part of that, I thoroughly enjoyed the work in optics, but I kind of decided that my life wasn't going to be spent working in a darkroom, and decided that I would prefer to be out in the open, and making measurements at sea seemed like a great wheeze, and I've thoroughly enjoyed that aspect of my career as well. There can't beat getting out in the cold and rain and the wet and actually making measurements at sea. It's my favourite bit. All through that career, the training as a physicist has been extremely important, and what we'll see in the course of this talk is that there's an awful lot of work to be done in trying to establish the quantitative nature of our data, trying to understand the data quality, because ultimately everything that we measure in the ocean is going to be used by modelers or by policymakers, and data quality is absolutely king in this. And so as we go through this talk, you'll see this feature coming up again and again and again. And it's something that I am working with my undergraduate students, my postgraduate students. It's a key feature of the background that we come from. So these are the sort of motivations that are driving me just now. And as I say, I'm very keen that the work that we do is useful and provides information that makes a difference in the long term. And I think there's a lot of work to be done on how we integrate our research efforts more fully with modelers and with policymakers. And that will come through, I hope, in this talk. What we're going to talk about today, well, the title of the talk is Light in the Sea. I'm going to skim through a few different areas. I'm going to start off by talking about the influence of natural light fields in ocean physics and biology. Light transcends both of those areas. It forms an important linkage between them, and I think that's one of the key things that I like about this, is the real genuine interdisciplinarity of it. I'm going to talk a little bit about how we can use light for ocean sensing, talk about some applications of ocean colour remote sensing. And Hannah, I think at this point, I was going to ask the audience here to give you an indication of how many of them have experience in using this kind of remote sensing data. How many of them have had some sort of exposure to it, just to get an idea of who I'm talking to here.
So for everyone who's an attendee, please select an option that is the right one for you, please. I'll give you a couple more seconds just to get those answers in.
I like I must be in the wrong seminar. Oh, good start. Excellent. I'm going to convert you by the end of this, honestly.
Okay, a couple more seconds, get those votes in.
Okay. So we've got 64% have some previous knowledge and experience. So that's a pretty well-informed audience. That's great. So I'll not try to go too far back into it. And I hope that what we talk about here will be sufficiently kind of self-explanatory that it'll appeal to most people. Thanks, Hannah. Okay, can I close that? Brilliant. Okay. So we're going to talk about ocean colour remote sensing. I'm going to talk then about some of the new developments that we're involved in, some of them involving heading off into places like the Arctic, that you can see in this picture here. We've been moving into some unexpected directions, which have been very exciting. And again, we'll finish off with just a wee view towards the future and how I think things are likely to develop in my field. Before we go on, I really must say thank you to all of the students and all of my collaborators that I have worked with over the many years that have contributed to the data presented in this project, in this presentation today, I should say. There really are far too many to be able to name everyone individually as we go along, but it's a heartfelt thanks to everyone. It really has been a pleasure to work with such a diverse group of people. It's been fantastic. So, where does light interact with oceanography? Well, the number one interaction for me is that light from the sun has the primary role of heating the ocean. We take maps of sea surface temperature like this, which we can get from satellite sensors, and you can see the warming of the equatorial regions and the cooler polar regions further north and further south. And that warming effect of the ocean plays a really important role in driving the thermohaline circulation. So the whole business of how the currents flow and as we head towards the poles, cool down and sink and get transferred all through the planet here, that's driven primarily by, it's light from the sun that is heating the ocean and pushing forward all of these massive ocean currents. So it's an integral part of defining the physical structure of the water column. But closer to my own main research interest, there's a huge interaction between light and ocean biology as well. And traditionally, a large part of that interest would come through the interaction with photosynthesis. Plants in the ocean using light to drive photosynthesis, bringing out carbon dioxide from the atmosphere and converting it into organic carbon to grow and to support the food chain, etc. And from maps like these, which again have been generated from ocean color remote sensing, we now know that there's almost as much primary production happening in the marine environment as there is on the land. So when we talk about how important the tropical rainforests are for the greenhouse effect, the same is true for the oceans, but the oceans are much more difficult to sample on a regular basis. You can only be in one spot at a time from a ship, whereas the satellites are giving us this much broader coverage. So it's really important that we're able to get these sorts of broad overviews of the planetary system. So the question then is, how did we get to a point where we were able to start generating these kinds of images? And this is where we start thinking about, well, how did we start understanding the role of light in the ocean, and how did we get from the early days to these very high performing technology of going into satellites in space? It actually goes back to a Jesuit priest back in the 1800s called Angelo Secchi, who wasn't an oceanographer at all. He was an astronomer, but he invented a thing called the Secchi disk, which is basically a white disk which you lower into the water column, and as you drop it down through the water column, you note the point at which it disappears from view because it's faded into the background illumination of the seawater. And from this very crude but actually very effective measurement, all of the other optical sensing technologies have developed. As I say, this was first used in about the 1860s. Since then, we have gone from the Secchi disk through underwater imaging, and then as you try to do the imaging, you realize that you have to try and understand how light is propagating through the water column. So you then start to look at how much light is being absorbed, how much light is being scattered, and we now have a whole bunch of sensors that we can deploy on optical rigs such as this, throw them off the side of a ship and either measure those optical properties themselves or the actual light fields. And we'll be talking about some of that kind of measurement later on as well. So we're now able to make measurements from the side of a ship that allow us to do a very good job of characterizing the optical properties of the water. And we have, in the last 20, 30 years now, entered into the satellite age, and we have satellite sensors in polar orbits primarily, circling the Earth every day, taking images of the ocean and the land and giving us daily global coverage. So every part of the ocean is observed on a daily basis from this fleet of satellite sensors. The sensors have now been in continuous operation since about 1997. So we're generating data sets that are of sufficient duration now, with multiple iterations through there, that we're starting to generate data that's climate relevant. We've got enough time series there to be able to start looking for trends associated with global climate change. Very interestingly, one of the things that we're starting to realize is that we can use the satellite data to predict second-disk depth and generate a time series that then goes back to the 1860s, which is even more interesting in terms of those climate change effects. I personally think it's just a kind of deliciously ironic aspect of what's happening here, that the highest technology is being used to go back to the simplest records that go back through the historic time period. So that's one of the little joys at the moment. So when I'm talking about the satellite sensing that I'm involved in, it's ocean color remote sensing that we're looking at. We're looking at the reflection of light from within the ocean and how that is being affected by the materials that are present in the water column. And one of the reasons why that's particularly exciting is that it gives us an insight into the biogeochemistry of the surface part of the ocean. We can see processes going on in the surface of the ocean involving phytoplankton growth and senescence. We can see plumes from rivers. There's all sorts of features that go on here. These sorts of images here, the animation that we have here, you can identify incredible features. If you look at, for example, the plume from the Amazon, there are periods where you can see that snaking out most of the way across the Atlantic. You can see El Nino, La Nina effects here in the Pacific. It's really a dramatic view of the planet over a decade in this image here. And as I say, we've now had this global coverage since 1997, and that's really becoming a very important part of our tool set for looking for effects of climate change on the ecosystem. So that's the point where you have these wonderful images where you think you can see everything that's going on in the ocean, and that was a map of chlorophyll in the ocean, and you think, well, that's really terrific. We're making huge strides forward here. Things are looking pretty positive. My job is to understand not just not just to present those sorts of images, but to look at those images as data and to understand the quality of that data. And that's really, really important, because once we get beyond trying to observe the patterns of behavior, we then have to try and quantify them, and that involves putting the data into models and trying to use it in a much more quantitative sense. And for that, we really have to understand how the measurement is made and do a lot of work on calibration and validation. So before you do that, you have to understand how that signal is generated. What we're looking at is light from the sun. It's being directed down towards the sea. And the bit of the light field that we really want to measure is this red line here, which has got into the water column, has interacted with the phytoplankton or the mineral particles or the dissolved organics that are inside that are suspended in the water. And some of that light has been reflected back up into space and been collected by the satellite. That's the signal that we really want to measure. As it happens, what the satellite actually measures is really dominated by this component here, the atmospheric scattering. Almost 50 to 90% of what's actually measured here is light reflected from the atmosphere. And so there's a really big job of trying to eliminate that atmospheric scattering accurately in order to get at this signal here. And once we can get to the signal from within the water column, then we can start to analyze what was actually in there. But the atmospheric correction, as we'll talk about in a wee minute or two, is extremely important, and particularly as we go into coastal waters, it gets harder and harder to do that right. So That's the nature of the measurement that we're making. We're looking at sunlight being reflected by the system. What does that look like when you get to the point of having made the measurement? Well, I've simulated 3 different scenarios here. If you look on here, we've got a graph showing wavelength, that's the color of the light, and this is the remote sensing reflectance coefficient. And if I start with open ocean waters, that's ocean waters with very low amounts of chlorophyll in it, even very clear blue waters. You can see that they're blue because the highest reflectance is here towards 400 nanometers. That's the blue end of the spectrum. And the reflectance dies off towards the red end because the water itself is absorbing in the red. As we increase the amount of chlorophyll in the water, the chlorophyll absorbs primarily in the blue-green, and we see a reduction in the reflection in this part of the spectrum here. So as I increase the chlorophyll concentration, the reflectance in the blue drops down as we increase that concentration. And you can see that there's almost a kind of pivot point here in the green. So most chlorophyll algorithms are based on looking at that ratio of blue to green reflectance. That's terrific. What then causes a problem in coastal waters is that we then start adding other materials that don't co-vary with the chlorophyll. And in this case here, I've simulated something like the Bristol Channel, where there's a lot of sediment in the water. And you see that that causes a massive increase in the overall reflectance of the system, and has a very strong drop towards the blue, because again, the sediment themselves also absorb in the blue. So there's a problem here, because the introduction of sediment also affects those blue-green reflectance ratios. I've shown full spectral data here, but in actual fact, the satellites that we use at the moment are multispectral, and we only have a small number of bands to work with. I've highlighted the bands here for MODIS. And it's only those measurements there that we have to work with in order to derive everything else that we want to know from space. Everything comes from a measurement of light after atmospheric correction and so on. And that's a real challenge. So it shouldn't be too much of a surprise that it's actually quite difficult to derive some of the more advanced products that you may have come across if you've been working with this data set before. One of the key targets is to be able to measure chlorophyll from space. As again, I showed you some of those images earlier on. There isn't a single chlorophyll algorithm. There are actually many chlorophyll algorithms of varying types. As I say, the majority of them operate on various combinations of these blue-green reflectance ratios. And there's a lovely paper here by John Riley and Jeremy Werdell, where they actually compare something, I can't see that because of the thing, it's 65 algorithms which are designed to work with 25 different satellite instruments. So they're doing a really comprehensive run through all of the various possibilities, trying to establish what are the optimal wave bands and combinations of wave bands to try and get the best quality product out. And what you see is, in actual fact, there's pretty good performance, and whilst there is variation from one algorithm to another, there's fairly comparable performance. The mission target is plus or minus 35%, and I'm going to talk a wee bit later about why I think that is. But if we could get to plus or minus 35% accuracy on the chlorophyll product, we would be very happy. These data sets are dominated, however, by open ocean water. And when we start to look at the performance in coastal waters and in shelf seas, things start to look a little bit different. This is some work that's currently underway. It's a PhD student of mine, Majid Hajjal, who's funded by MASTS and the Data Lab, and we're working very closely with Marine Scotland on this one. And the point here is we're trying to understand the quality of the data that comes from ocean colour chlorophyll algorithms when we look at areas like the North Sea, coastal waters around Scotland, and areas where where we have a statutory responsibility to report against environmental legislation. This is a potentially terrific data set, a wonderful tool to support those kinds of activities, but only if the data quality is of sufficient accuracy that we can trust the data that is produced. So this is Northwest European shelf seas. On the x-axis, we have a set of that have been provided for us by Marine Scotland and ICES. So it's covering a large area, a long period of time, lots and lots of samples. And what Majid has done is he's gone into the satellite time series, identified potential matchups, and applied one of the leading chlorophyll algorithms for this type of area. And what we get on this log plot here, so we're going from, we've got 2 orders of magnitude on each axis. What we get here is some sort of relationship between what the satellite is predicting and what was actually measured in situ. The black line is the 1-to-1 line, and the inner dashed line is plus or minus 35%. The outer dashed line is plus or minus 100%. Now, there is clearly a degree of convergence of some sort, but I think it would be stretching credulity to say that that was a strong relationship, or the sort of data that you would really be comfortable staking the reputation of your environmental policy on. And that's a real problem. We have a major issue here. Whilst those images do reveal important processes, you can see these things happening. In terms of actual quantitative data, I don't think the data that we're looking at here is of sufficient quality. And we really, really need to spend time and effort and frankly money looking at how to try and improve this. The opportunity from space is fantastic, but we cannot leave it at this level here. Why are we having these problems? Well, we're dealing with a very complex area. We're looking at areas where there's inorganic materials, mineral particles at varying concentrations and different seasonal effects. We're looking at dissolved organics coming in the river systems as well. And all of those things tend to have an impact on the performance of these kinds of algorithms. What I should say though is that by using our radiative transfer modeling techniques, we know that the effect of those materials would typically be to cause an overestimation of the chlorophyll. And what we see here is not just overestimations, but also a significant amount of underestimation as well. And that's where I am very much thinking that one of the major problems that's outstanding here is that the atmospheric correction, which defines the quality of the data that goes into the algorithm, is also suspect. And that's not a surprise, because the atmospheric correction in these kinds of coastal water is also affected by the presence of these types of materials. So we have a long way to go. And it's very difficult to give a presentation like this that sounds as negative, but we really do need to put more work into understanding this and improving the quality of it if we're going to be able to exploit this technology to its true extent. I should also point out, however, that we also have to understand the quality of the X values here, the in situ chlorophyll data. And I want to take you to a data set that we collected in the Mediterranean a few years ago, a good few years ago now. And on this cruise, we had a very unusual situation where we had sets of teams making duplicate measurements of each of the parameters. It was a really unusual cruise for that. So what this means is we had 2 teams measuring chlorophyll from the same bottles as they were coming out of the ocean. And that doesn't happen very often. There are dedicated round robin experiments that do this, but it doesn't happen very often. So one lab measured chlorophyll on this axis, another lab measured chlorophyll on this axis. These were all HPLC samples. It was high quality stuff. And you see that for the majority of points, you see these, majority of these points here, the data set follows the 1-to-1 line pretty well. It's doing not too bad, it's close. However, there are these points either side that are obviously look like outliers, but you only know that these ones are outliers because you've made the duplicate measurement. If you look at the the relative percentage differences from that, the range of uncertainty on those in situ chlorophyll values is plus or minus 40%. And that's much higher than most people realise. In fact, if you look at the round robin studies that exist in the literature, that's actually the sort of number that's coming out of them. So the in situ validation data is also a limiting factor, and we have to factor that into what's a reasonable expectation of performance. And I would say that this uncertainty on the validation data is a large part of why we have a mission target of about plus or minus 35%, because I don't think we can do the in situ measurements any better than that. There will be people who might disagree, but that's what the round robins are actually telling us. So, coming back to the pretty pictures and how we would go about interpreting them, here's one of the classic images of the west coast of the UK and Ireland, and it's an absolutely phenomenal picture. I can see so many features going on in here. They're absolutely stunning. The physical oceanography mixing on with the biology is glorious. How much of this would you actually believe in terms of quantitative measurements, though? To me, I believe the data is pretty good out in these open waters here. We've got a lovely coccolithophore bloom going here. That could actually be a wee bit tricky, but out in these sorts of areas here, where we're away from the main sources of confounding materials, it probably works quite well. However, as you go into these coastal areas, here in the west coast, where we probably have quite a lot of dissolved organics coming in with the fresh water, the Irish Sea, where we have lots of sediment resuspension going on, the Bristol Channel, round here in the English Channel and further round into the Thames Estuary. These are areas where there's a huge amount of sediment in the water, and it just confounds the algorithms very badly. So the take home from this is due caution is required, and there is still a lot of work to be done here. In my own group, we have a PhD student looking at a spectral deconvolution technique, which is where we use a bio-optical model that takes into account all of these additional materials and tries to extract out a more realistic estimation of both the chlorophyll and the minerals and the dissolved organics. And that's working quite well using in situ data. But again, when we try to do this with remote sensing data, the atmospheric correction is the limiting factor here. And we really need to get into atmospheric correction for these kinds of areas and much more seriously. We're also looking at machine learning approaches. And again, this goes back to Majid's PhD. And there's real scope here, I think, to combine the atmospheric correction in with the algorithm to retrieve chlorophyll and perhaps find new approaches to deal with this fairly major problem with atmospheric correction. So I think there are real grounds for thinking we can do better than we currently are, and the tools to address this are coming online. What else can we see from space? So I'm going to start talking about that area there was the sort of traditional area that we've worked in for a long, long time. I'm going to start talking about some of the more emerging areas that we're getting involved in. And one of these involves an entirely different class of particles altogether. I was approached by colleagues in the University of the Arctic in Tromsø and asked about the possibility of being able to identify zooplankton swarms from remote sensing. Basically, they have a major fishery in this part of the world, which depends on a key life stage there is these huge swarms of Calanus finmarchicus, a small zooplankton. And we'd never really had anything to do with anything higher up the trophic chain than phytoplankton, so it seemed like quite an unusual kind of development to try and get involved in. What threw it for me, what made me interested, was reports of the water being visually to the naked eye pink. And if your eye can see that the water is pink, then you would expect that would be sufficient to, if it's on a big enough scale, that it would be sufficient for the satellite to be able to see it as well. And what we have discovered is that if we go out to this area here, so this is the Lofoten Islands on the northwest coast of Norway. This is the continental shelf runs around about here. And what we discovered when we went out here and were being supplied with data, real live data from the satellites by NEODAS, based down at PML, was that the RGB, the red, green, blue images were highlighting areas with red pixels in this shelf edge area here. And when we went into these areas and did net sampling and camera sampling and like, we discovered that in actual fact, these were areas where we found very high concentrations of Calanus right at the very surface, where they have the potential to influence the remote sensing reflecting signal. And the way in which we think this occurs is that if you actually look at the animals under a microscope, very often you see that they have patches of this red pigment, astaxanthin, which, if you have enough of them in enough concentration, eventually causes a change in the overall colour of the water. What we did on that cruise was we took a sensor called a SciCam. It's a point source integrating cavity absorption meter. It's a very unusual sensor for measuring absorption, and one of the beauties of it is that it allows us to measure the absorption of highly scattering materials, such as we encounter in the marine environment. The sensor is shown here. My PhD student at the time, Ina Leifring, took individual animals, started adding them one after another in a serial addition experiment into the cavity, and was measuring the absorption as we increased that concentration. And as you can see, the absorption increased into the blue. And when we then did a linear regression of this, we see that we can predict the absorption per unit animal, and there is this strong peak in the blue-green associated with, we believe, the astaxanthin content of the animals. This is a fairly radical new observation. We haven't worked in this area before. We're still trying to understand exactly how much effect the animals have on the overall radiative transfer. It's a very challenging environment. Normally, when we put sensors into the water, we just get to measure whatever's there. In this case, the thing that you're trying to measure actively swims away from you, because you put the instruments in the water and they try to evade them. So there's a whole series of new challenges that we're having to face, trying to make measurements, quantitative measurements at that, on this type of sample. Moreover, the problem, that one of the reasons why we haven't seen this before is potentially that the sensors that we use to make these measurements are designed to look at things like phytoplankton and sediments and so on, which occur in high numerical abundances, whereas these things, even in a swarm, are relatively sparse. You're talking about 10 to 100 of these things per litre max, and that's assuming that you're actually sampling them at all. So there's a real measurement challenge to be addressed here. Nonetheless, the idea that we might be able to quantify these swarms from space is potentially highly valuable. These animals are being commercially harvested as well, so there's real merit in being able to try and quantify these species on the kinds of scales that you can only get from satellites. We're moving a bit further north. It has been a fascinating couple of years. We've become involved in a number of projects that are taking us right up, even further north than the Lofoten Islands. And one of these is Arctic Prize, which is part of the NERC Changing Arctic Ocean programme. And this has taken us all the way up to Svalbard, and in some cases beyond. The Arctic is a fascinating place. It's actually probably one of the hottest topics in oceanography today. It is warming faster than any other part of the planet, thanks to climate change, and we are witnessing an ecosystem going through a period of unprecedented change incredibly quickly. So it's a real privilege to be able to go and get involved in part of the work to try and document that, to try and understand what's going on there. It's also really quite sobering to do so. What we've been involved in as an optics group is looking at light. We're interested in light in that environment and how it is affected by the changing properties of primarily we're looking here in the Barents Sea, and how that influences the growth of phytoplankton blooms and through the spring and summer, and the formation of water column structures and so on. One of the difficulties of working in the Arctic, though, is that it is particularly cloudy. You think it's bad in the west coast of Scotland, it's even worse up there. And so, although we have satellites covering it every day, we don't get to see through the clouds, and having access to reliable data sources that can make observations during those cloudy periods is vital. And one of the beautiful things that the prize team were able to put together was working with NOC, getting gliders deployed into the Barents Sea and transiting up and down through the different latitudes over a period of about 6 months, allowing us to document the transition from Arctic night through to 24-hour daylight in the summer, and all of the changes that involves in terms of phytoplankton blooms and dying and deep blooms forming later on in the season. In order to fully exploit that, we really do, however, need to try and form links between what the gliders can measure and what the satellites are able to see. And this is the sort of thing, you see these lovely diagrams of we'll deploy gliders, we'll have satellites, and it's all 21st century oceanography. It's really, really exciting. But at some point, you have to make sure that the data sets that are being generated are mutually consistent. And one of the things that we've done early on here is to try and establish that. So what we're wanting to do here is, can we establish quantitative links between the satellite data and what these AUVs are able to tell us? Excuse me, I've just gone forward again. We have here a plan, and we take data from the glider, which in this case is backscattering and fluorescence data from one of the small sensors that's mounted on there, and also salinity from the CTD. We can use that to generate estimates of the chlorophyll concentration and the dissolved organic concentration. From there, we can put that into a bio-optical model that we've developed based on our shipboard measurements at 3 different points through the season. And having generated that, we can predict what the remote sensing reflectances should be and see if what we're predicting from the glider matches in any sort of way what the sort of reflecting signals that we get from the satellites. I'm going to show you some data from one of the transects. So this is Svalbard, away up in the far north. This is the line of the transect by the glider. This took from the 27th of April to the 12th of May. So you got a couple of weeks worth of data in this north-going transect. And as we went north along here, we have, I'm just going to move that picture there. We have changing temperature on the top panel. So as you see, as we go north, the temperature gets colder and colder, and around about here, around about 75.7 or thereabouts, we cross over a polar front into much colder water, and some of these waters here are below zero. As we go through that polar front, there's also a change in salinity associated with the ice cover there, and we also see changes in the particulate backscattering in that area, which is associated with chlorophyll fluorescence and a phytoplankton bloom north of the polar front. We can take that data now and we can convert it using the process we just talked about into estimates of the water absorption in the blue and the absorption in the red, in fact all of the wavelengths, and also into the scattering at all different wavelengths as well. So we've now got a means of taking this kind of raw data from the satellite and turning it into quantitative estimates of bulk optical properties. And if we know those bulk optical properties, we can then put them into the models for remote sensing reflectance. And what we get here is a set of data that we've managed to collect from one image from the satellite. During the middle of that transect, we got a set of data that looked like this. So again, this is wavelength on the x-axis, remote sensing reflectance on the y-axis, and you can see that the majority of the data is bouncing around 1 per steradian in the blue-green, and then dropping down as you go into the red. These are some outlier points higher up. we see similar, but not exactly the same data from the glider. And clearly there are points that are present in the satellite image that we didn't encounter with the glider. The model's not perfect, but it's getting us pretty close. And what we want to do now is be able to take that bio-optical model, which we can show is tolerably close to what you see from the satellites, and use that to drive light field models. And we'll work with the modelling group here at Strathclyde, run by Neil Banas, to update their optical models and improve the parameterization of the light fields in there, and hopefully improve the parameterization of algal growth through that season. And having access to all of these different sources of data is absolutely vital to do that. So working in the Arctic was a challenge, and then it got one stage further. We found ourselves working in the Arctic in the middle of winter. This is one of the reasons why I actually really wanted to get into this field. It takes you to places that you would never otherwise get to go to, and it really is the most exciting environment to work in. We, as part of Arctic Prize, and then more recently through a Norwegian funded project called Deep Impact, we have an opportunity to go into the Arctic, up in the Barents Sea and in the coastal waters around Svalbard, and look at how that system is affected by the very small amounts of light that exist in that area at that time of year. And very importantly, how that is perturbed by the presence of a brightly lit ship from which you're trying to do animal surveys. It has to be said, this is an extremely challenging area to work in, both in terms of just the general conditions that you know, it's very cold, it's very dark, and trying to make light measurements in this environment is really pushing our sensors to the absolute extreme, so much so that we're having to start to develop new, even more sensitive sensors that will allow us to work in this environment. So we're looking at the polar night. There are months of darkness here, during which time the animals that inhabit that part of the world are exposed to extremely low light levels, but not necessarily zero. It's not totally dark. There's moonlight, there's the aurora, there's starlight, there are sources of light there. And increasingly you have ships and expanding human settlements generating artificial light. And that is potentially going to have an impact on an otherwise relatively pristine light climate. So, as I say, very challenging environment to work in. The first time we were there, we were joined on board by a film crew who have turned this into a record of a documentary of the cruise into a movie, which is appearing at festivals around the planet, where it was until COVID struck. I have to say, one of the most uncomfortable experiences of my life was hearing myself talking on that movie, and I guarantee I'll not be looking at the recording of this either. But if you get a chance to see it, it gives you it really does capture very well how difficult it is to work in this particular environment. I've got a couple of images here just to try and convey that. This is on the Helmer Hansen. I've got a bunch of light sensors here. We're trying to measure the light levels coming from the ship. And in particular, we're looking at the effect of the lights that are being directly shone into the water, which is where we would be normally deploying nets and profiling gear, etc. So I'm trying to get this instrument here to operate in the brightly lit part of the water there and see how far down into the water column that light penetrates. As you can see, it's a snow and ice covered deck. The conditions are pretty wild. And, you know, 1 minute you've got this nice clear environment to go into, and then a few minutes later, especially when you're working in the fjords, in comes the ice, and all of a sudden you're left with it. Oh my God, how the hell am I going to get that instrument cage back out of there without trashing all the sensors? It's a very, very scary place to put expensive equipment into the water. We managed it. We've managed to do it without any serious damage, not too much serious damage, but it's certainly forcing us to revise some of our plans before we do it again. What did we find? Well, I'm going to show you some data here from a recent publication where we are looking at, on this plot here, we're looking at acoustic profiles. So this is acoustic data from the ship's sonar system. You can see at the start of the time series here, we have the ship's lights are off. Can't see if I can get my, oh, hang on. Here we have the lights are off, and we take a time series of that, and then we switch the ship's lights on. And what you see is an instantaneous response all the way down to 200 meters of different, and these are different frequencies corresponding to different sizes of animals in the water, fish down to zooplankton. And all through that 200 meters of water, there's an instantaneous response. And that tells you that we are seeing a very significant perturbation of the system from a brightly lit ship coming up through an otherwise very dark area. And there therefore has to be a question about what sort of impact might that have on attempts to do nighttime surveys and so on. And I think there's an interesting question there for which we don't really have the final answer, but it's certainly interesting that we're seeing these sorts of effects. Our job was to measure the optical properties of the water and to predict the light levels all the way down to those depths. And it has to be said, even though the water is absolutely crystal clear after months of darkness, down at 200 meters, the light levels that we're predicting are still very, very small. You're looking at photon counting almost. So it's interesting we'll have to try and work out, do the animals have sufficient sensitivity to see these small light levels, or are there other effects in addition to the actual light itself? Is the response purely visual? And I think there's lots of open questions here that I don't really have an answer to right at this moment, but we will be doing further research into. So, as if that wasn't hard enough, at least there we were trying to measure the ship's lights that are quite bright. And in the last area that I'm really going to talk about of new areas we've got into, we're now being asked to get involved in trying to measure the artificial light from towns and cities on the coast, and trying to understand how much impact that might have on animal life in shallow waters near to the coast. And this is a big issue because there's been a massive increase in the amount of population along the coastlines globally, and in the amount of light being directed into the sky. You got an image here, you can see the kind of orangey sky glow above Plymouth, and we're using the sensors to try and measure that, and then we try and propagate those measurements again down through the water column numerically, because the existing sensors that we have are not sufficiently sensitive to measure this small amount of light all the way down, and there's a real opportunity here to try and develop new sensors that do have that sensitivity. The overall aim of this is to generate maps of the spectral light distribution at the seabed. We're primarily interested on what's happening on the seabed. That's also a function of the bathymetry and the tidal state. So it really becomes quite a multi-dimensional problem to try and solve. We're in the early stages of this. But the idea is, can we identify areas that are vulnerable to light pollution and use that to perhaps help guide policy on street lighting schemes in these kinds of areas? We've got some results that are now in press, and what we have here, this initial study was done in Plymouth Sound, down in the southwest of England. We have divided it into blue light, green light, and red light, and the blue light is particularly important in terms of the sensitivity of eyes of creatures of interest. This is it starts off with the depth, mean high water, mean low water, and we're looking at the areas here that are dark are not being affected, but the light areas are areas where there is a significant impact from the light levels we were measuring near the sea surface. And this is a new area of research for us. There's growing interest in it. There's a growing appreciation that there are potential negative effects of this, and growing efforts to try and mitigate where we can, and to at least just understand what those effects might be. At the moment, we're going to be working down in that southwest corner of England with colleagues from PML and Plymouth University. But the idea is that we can also use satellite data of nighttime light levels to start generating global distributions of this artificial light at night and how it might affect different areas of coastal waters. So that's pretty much where we're at with that one. So this time seems to have flown past for me. I hope it's okay for you guys. I'm going to talk about some future perspectives, where I think this area is going to go. In terms of remote sensing, I'm thinking here of ocean colour remote sensing, I think we're already beginning to see the advent of hyperspectral sensors being put into orbit. That's filling in the gaps between those spectral bands that we talked about earlier on. That will have benefits in terms of being able to resolve unusual features, particular pigments, for example. We are also already beginning to see the advent of much higher spatial resolution data. We're now able to routinely get Sentinel-2 data at 10-meter resolution, which is absolutely fascinating and is extremely important if you want to get into coastal areas such as the west coast of Scotland, where we have long, narrow fjords, and I think that's an opportunity that we will want to try and exploit very quickly. We typically get very few passes per day. You're in sun-synchronous orbits, so you only get one bite at it from most sensors. I think we will see a change in that. I think we will see constellations of small satellites being launched, which will give us a much higher repeat visit frequency and will allow us to exploit gaps in clouds and things like that. And we will see more and more data become available. Similarly, geostationary platforms and even high altitude platforms are going to feature and provide. There's going to be data coming from all sorts of different sources. The key thing in all of that, though, is that we need to understand the data quality. We're going to have to, having the raw data is terrific, but you need to be able to turn it into high quality products that end users can trust and at least understand what the quality is. For that, I think we are increasingly going to be looking at using machine learning algorithms, as I say, particularly to deal with the atmospheric correction. That won't replace, all of that data will not replace the need to go out and make measurements at sea. That will never go away. All of these algorithms, particularly for machine learning, will need constant updating for the training and validation. So there's no end to seagoing oceanography in my book. I think all of these things are complementary to that, and it's the maximizing the potential and the return on both that we're going to be faced with. And as I say, in all of this, data quality is king. We really need to focus effort on establishing that data quality. In terms of sensing, miniaturization is the name of the day. There's going to be all these lovely platforms and that are available, but need sensors that will have to be developed specifically to work on them. And so miniaturization for AUV deployments is a big thing. I also think that in terms of optics, there's a technique called LiDAR, where you use laser beams fired into the water or into the atmosphere and look at the return signals coming from them. I think there's great opportunity to use them on surface AUVs and to even on underwater AUVs and extend the reach of your measurement capability significantly. I think this is a big area for us in marine optics that is really going to come into its own very soon. The work we did in the polar night, where we integrated acoustics and optics, is very interesting. I think particularly as we start looking at zooplankton, being able to make measurements using both techniques simultaneously is going to be very important. And I'm very excited about the whole prospect of bringing those two trophic levels within the sphere of what we can measure using these techniques. And just a plug here as well, the availability of 3D printing and cheap electronics and cheap cameras and all the rest of it, has tremendous potential, absolutely tremendous potential to make sensors available on a much lower cost basis than they have been previously, and to allow people to effectively build their own. I'm showing you an image here of a 3D printed microscope, which we've recently published data from, real good high quality data from a microscope that cost, its lowest cost version was a couple of £100 to put together. It really is remarkable what you're able to do now. And I think there's going to be much more of that going on. And I think it's extremely important that we're able to do that so that we can get technology into the hands of the public users in developing nations, lots of areas where people are currently excluded from being able to access the technology. These sorts of things really need to be exploited to maximise uptake wherever possible. I would also say, and this comes back to working in a physics department, that one of the things that I've enjoyed most in the last few years has been an opportunity to work with people in my own department and elsewhere, looking at new technologies that are emerging in their lines of research, in photonics, for example. And in the case I'm talking about here is quantum technology hubs. There's amazing new technologies being developed in other areas. And oceanography, in its widest sense, is potentially a terrific environment for these kinds of groups to test their equipment and show what it's capable of in real world environments with real world applications. And one of the take home messages from this is that we really do have an opportunity here to talk to our colleagues in different disciplines, and by doing so open up new areas of research that are really very, very exciting. I'm almost at the end. You'll be glad to know. I'm going to bang on about it. Data quality is king. If we want, as optical oceanographers, people to use our data, then we have to be able to ensure the quality of it and allow people to have confidence in what value that product actually has. To do that, we need to deal with data uncertainties. We need to know what that data quality is. It's the sort of argument that I have with my undergraduate physics students, and I can point to this field as being a terrific example of where this is absolutely vital. As a physicist, one of the things I'm trying to get across to my students is you need to understand your instruments. You need to know how your sensor lies to you. You think you've measured something, but have you really? What is the uncertainty in it? Do you understand how it may have done something that you didn't intend it to do? And that's a real key part of everything that we're trying to do in this area here. I said at the start that I'm really interested in trying to make sure that the data we produce is useful and gets used, and that data quality thing is an extremely important part of that, but it's not the only part. Very often, I think we do research proposals that are based on that which is feasible. And we start from the observations and hope that someplace at the far end of it, somebody's going to be sufficiently interested in it that they'll be able to put it into a model, or it will somehow have influence in policy. That's fine for blue skies research. I think that's not as bad as perhaps I made it sound there. However, there is also scope for us to restructure some of our work and really build in the end user from the absolute outset. And I think having conversations that involve end users, the modelers and the observationalists are much less frequent than they should be. And there's a real opportunity, I think, to look at what does a policymaker actually require? What sort of model output do they need in order to address the questions that they want to do? And then for the modelers to say, well, in actual fact, I need the following parameters. Like, for example, I need growth rates, I need grazing rates. Are we actually measuring these things at sea? Well, very seldom, very, very seldom. And the modelers can talk to the observationalists like myself about what it is they actually need. And there's a real open door here, I think, for us to set up new conversations that will open up new areas of research. I'm very excited about the future. And the last thing I would say then is that I'm very grateful to be part of MASTS. MASTS has been a terrific opportunity for me working in a physics department to have conversations that jump across the discipline boundaries and have allowed us to stimulate these new areas of research that I really couldn't have anticipated 10 years ago, and over the last 3-4 years have opened up exciting new doors that I'm very pleased to be involved in, and have set up new collaborations that I really think are going to be extremely productive in the long run. So I think MASTS is working. I think it's a terrific effort that we should all be proud to be part of. So thanks very much. That's me done.
Great. Thank you so much, David, for the really nice summary slide with some excellent points that I think you raised as well. And just to kind of mention what you also said in that summary slide, it's great to see data coming from studies that have been testing different methods against one another. For instance, that trial that you said that looked at the 2 results that came from 2 different labs. That's just a really great thing to see that is happening, not just taking one set of results from one type of analysis and just taking it as it is. I really like seeing that comparison, and also just the constant reiteration that actually we need to make sure that we're using really good data and just using those different methods, seeing what's working. How do things compare to one another? What can we learn from different methods as well, which is really great. We've got a couple of questions already submitted for any of our remaining attendees. If you have a question that you would like to ask David, please pop it in the Q&A at the bottom of the screen. This entire session is being recorded, so if you hear an answer that you would like to replay, it will be up on the MASTS YouTube page at the end of today once we've finished this entire session. So David, we'll just leap straight into that first question that was submitted, and that was came in very early into your talk. So that was asking, what are the most common mistakes / misunderstandings that people make new to RS make when trying to use RS data in their work? For instance, SST, color, etc. If you could just explain what RS might stand for, that would be really helpful as well, please.
So RS in this case means remote sensing, and I think it's a very good question. I think the answer to that from my perspective is simply to believe what they're being presented with at face value. I think in many cases we see images from these sorts of platforms, and it looks to us like an image in the same sort of way as a photograph perhaps, or a map perhaps. And we're not used to really questioning the values of pixels on either of those sorts of things. For the kind of data that we're working with, it really is very, very important to be sure that what you're being presented with is genuinely quantitative. And there are large parts, in our case, there's large parts of the ocean, the deep ocean, where I really wouldn't have too much worry about that. It all becomes much more tricky in coastal waters where the optical complexity is much more significant, and where it really becomes much more of a challenge to get those numbers right. So, but I think this is true not just for remote sensing. I think it's true for most things. We should always be looking at our data sets and saying, right, I've made the measurement, but how accurate is this? Can I get a handle on this? And just as you were saying a wee second ago, it's very seldom that, particularly in oceanography, where it's so expensive to get to see and to make the measurements, it's very seldom that we get to do those sorts of checks using independent measurements alongside us. And I think there's a lot of scope to do more of that work if we possibly can, and build confidence in ourselves about what's going on there. And that's going to come into the answer to the next question as well.
I have a question personally from me, and I apologize if you've already kind of mentioned this, but very much at the beginning you were saying how different coastal water is for measurement, how tricky it is compared to those deep open seas. And I was wondering, how far away from the coast, or how deep does the water need to be for you to kind of start picking up that these are good results? We're not being too impacted by the fact that it's coastal. I was wondering, what is it, or is it just so dependent on the area, really?
It does depend on the area to some extent, but if you wanted a general rule of thumb, I would say once you're onto the continental shelf, there's at least potential for you to be getting resuspended sediments coming up from the bottom, and if you're close to shore, sediments coming from river systems or estuaries or whatever. You start wondering at that stage, okay, is this nice clear blue surface water, or have we got the other materials causing a significant contribution? And as soon as you do, it starts to impact on those kinds of algorithms. Now, don't get me wrong, the people are working hard to try and adapt those algorithms to make them more robust, but the evidence that we are seeing at the moment is that there's still a long way to go.
Understood. Great, thank you. The second question was, why are values varying by 40% from these comparative measurements of chlorophyll? What are we getting wrong in the lab?
Very good question. I think we need to be very careful about how we do all parts of the sample handling. If you think about a coastal water sample, if you've got even a small clump of something in one sample that's not in the other, you will perturb it. The extent to which you're getting equivalent extraction of the chlorophyll is an issue. I mean, I'm not an expert on making those chlorophyll measurements. I would hasten to add, and people do make tremendous efforts to do it extremely well. The two labs that contributed to that data plot there, one of them was Horn Point, who do the HPLCs for NASA. You know, I mean, these are serious players in the game. I think that there are just genuinely, you know, fundamental limits to how well you can make that measurement. And it's not a criticism of the people that are making it. It's not even necessarily a critique of the techniques as such. I think it's just that we have to understand what the level actually is. And I could see a few things that I think might help, but I'm not really sure that they would. And I think at this stage, just having that understanding of where the levels actually are, and for us, how that propagates when we then use those data points. If I use those data points as is, then the uncertainty that's in them propagates into everything else. If I'm a chlorophyll specific absorption, or if I put it into a photosynthesis model, that error is propagating, and every time you do it is expanding, and that's just life. So I'm not trying to be particularly critical of those operators or the technique, but I do think that we have to get to grips with what the numbers actually are.
Great, thank you. The next question from Ricardo refers to the North Sea, and they say, for the North Sea relationship between in situ and satellite chlorophyll, have you tried to include an interaction effect so the linear relationship varies smoothly with solar zenith angles?
Not totally sure I follow that one, but what I would say is that the data set that we've been working with, we have got all the solar zenith angle information in there, and in fact the plot that I showed earlier on, the data had been partitioned by the solar zenith angle. There are potentially issues associated with the angle, but we weren't seeing a significant trend associated with that. The spread was actually quite wide, and in that sense, I think whilst there might be a solar zenith angle effect, the concern I would have would be more to do with the atmospheric correction, in terms of if we have even relatively small errors in that atmospheric correction, we're changing the quality of that spectral information, which then goes into the algorithm. And at that point, we've started to do a little bit of analysis of that, and it doesn't have to be a very big error before you get potentially quite significant effects. And what makes me think that might be the biggest problem here is that the nature of that error, either an overestimation or an underestimation of the reflecting signal, is what's needed to explain both overestimates and underestimates of the chlorophyll. If it was just the dissolved organics or the sediments, they tend to cause overestimates only. And it's the fact that we're seeing errors on both sides could be explained, I think, from the atmospheric correction. So that's it's an area that we're still working on. It's very much preliminary data, but it's certainly looking that way for us just now.
Great, thank you, David. We've reached the end of the questions that have been submitted, but if anyone has any questions that they would like to ask David directly, his email is on the screen right there, just on the bottom left. Thank you so much, David, for being today's MASTS webinar. It sounds like you have got a lot going on, including featuring in a film, which is always really fun to hear of MASTS member being there. You must let us know when that gets fully circulated online. And yeah, thank you so much. That was a really great in-depth and also hugely broad talk that you did. So that was really interesting, and I hope everyone really enjoyed that who is still with us. And as I said, it was recorded, so if there's anything that you would like to look back on, please check out the MASTS YouTube page at the end of today where the video will be. Thank you very much, David.
Thanks very much. Bye-bye now.
For anyone who is still with us, please check out the upcoming talks that we have as part of the MASTS webinar series. We are ending on the 2nd of September because the MASTS annual science meeting is happening from the 5th to the 9th of October. If you would like to talk at the MASTS annual science meeting, you have just a couple of days left to talk, to submit an abstract before we close our deadline. So that is the 14th of August. Please check out the MASTS website, MASTS Annual Science Meeting tab, for more information about how you can get involved in the MASTS Annual Science Meeting and feature in our programme. But until then, please check out the remaining webinars that we have coming up by just clicking the same registration link that you used to register for this very talk, and we hope we can see you then.